Okay, thanks for the introduction. I'm Hong Hu, a postdoc from Georgia Tech. So today I want to share our work on control flow integrity, which will enforce the unique code target property. So first, what is a control flow attack? So you can view control flow, the order of instruction execution. So attackers are going to use memory error to divert the control flow, which means they are going to change the order of executions. Because our program are going to use so-called indirect control flow transfer instructions to decide the target. For example, indirect function call, indirect jump, and a retain instruction. So attackers just corrupt the function pointer or retain address in memory to some malicious code address, like shellcode address or RP gadget address. So the control flow attack is the most common attack method these days. So the good news is control flow attack is getting harder these days because we have so many defense mechanisms now. And the most important one is called control flow integrity, or CFI. So the basic idea of CFI is we statically draw the control flow graph of the program. So this is a expected control flow graph by developers. And at a runtime, we will check whether the real execution will be consistent with the expected control flow graph. So any difference will indicate an attack, and we're going to block them. So over the years, we have so many CFI proposals from coarse-grained CFI to fine-grained CFI. However, control flow attack is still possible. So over the years, we have seen so many attacks, so-called the advanced control flow attacks. So they're like the out-of-control attack and the Cooper attack, control flow binding, and the control jujutsu. And the reason we still have attacks is under this control flow integrity, the allowed target is still much larger than the real valid target for a particular input. So we want to ask this question: what is the end of the story? What is the end of the competition between defenders and attackers? So the answer is clear. As long as we can enforce the only unique target, only unique control flow for each input, we can win the war. In another way, we can say for each indirect control flow transfer, we only allow one target. So this is our work I'm going to show you called UCFI. So UCFI are going to enforce the unique code target property, which means we only allow one target at runtime for each indirect control flow transfer. And our enforcement is quite efficient. It's only 80% overhead for spec benchmark and 4% for NGX web server and less than 1% overhead for some file servers. So let me show you some examples of attacks and existing defense first. So this program has a very classical stack-based buffer flow. So here we have a string copy. We'll copy the user input into a fixed size stack buffer. So attackers can corrupt any local variables on the stack, including this pointer fun here. So when the program performs this indirect function call, attackers can jump to any location, including this system and protect, exec, and setuid is critical libraries. So this is a very common control flow attack. And the control flow integrity, as we just mentioned, are going to identify valid target site for each indirect control flow transfer. And at runtime, they're going to check whether the real target is within this site or not. If so, they're going to allow the execution. Otherwise, they're going to abort the execution to prevent attacks. So apparently, if you have a larger valid target site, so attackers will have more flexibility to manipulate the control flow. So in this example, if we do not have any control flow integrity solution, so attackers can jump to any location. So if you have the type-based CFI, which means the target should have the same type as the call site. So in this case, it will allow 5 targets, including function A, B, C, D, and E, because all of them have the same type as the call site. So if you consider some perfect static control flow integrity, it will allow 3 targets here, because the static analysis will tell you this indirect call at line 16 will allow 3 targets at runtime. So what if we consider some dynamic information, like PyCFI? PyCFI will only allow address taken targets at the time of indirect call. So in this case, it will allow 4 targets here, including A, B, C, and D, because there has been address taken at line 5 and 6. So the most recent work called PDPAD will allow 2 targets. It will use control flow information to infer what should be the allowed target at the runtime. But if the ID is 1 here, the execution will go to line 14. And here I'm going to retrieve the pointer from the array, and the ID can be 1 or 2, so the target could be function B or C here. So you can see existing solutions field to enforce the unique target. And this is our goal of UCFI here. So UCFI defines a property called unique code target property, which means for each invocation of an indirect control flow transfer, there is one and only one allowed target. So this way, we are going to win the war against attackers. So the idea to enforce the unique code target property is to collect necessary control flow information, runtime information to infer the unique target. For example, in the code, if we know we run this particular line, so we know the first element of the array are going to be initialized as the address of function A, and similar to other elements of the array. And also, if we run this line, we will know the function pointer are going to be initialized as a non-pointer. And if we go to this line, if we know the value of ID, we can infer the unique target here. And then at the time of indirect function call, we will know which particular function is expected and others are malicious. So previous work PDPAT used the same methodology to infer the target. However, they failed to enforce the unique code target property because they only use Intel PT to get the control flow information. So the challenge of Intel PT is it only gets the control flow data, including two packages. First one is the TNT packet, which tells you for a conditional branch, it is taken or non-taken. And also TIP packet will tell you what is the concrete target for one indirect control flow transfer. So this is the only control data. So the first challenge is it fails to enforce the unique target. For example, here, the line 14, if you do not know the value of ID, you cannot tell which one is the real target you want to use. So here, the set size is 2, including function B and C. However, in some real programs we evaluate, like the Go benchmark in spec, it can have up to 479 functions in this site. So which means attackers can jump to any one of it to build attacks. So the second challenge is ptrace is efficient, but if you want to reconstruct the control flow from ptrace, it's pretty slow. So based on our simple evaluation, it can be 30 times slowed down for some SGM programs in spec. So now I'm going to show you our solution of these two challenges. Then we can achieve the protection efficiently. So first one, our proposal UCFI enforce the unique code target. So the idea is to dump the non-control data information using Intel PT by encoding them into some indirect control flow transfer. For example, if you want to know the ID value here, so we just instrument code with this particular lines of code. So we just plus the value of ID into some base pointer to create a new pointer. And as long as the pointer is within the boundary, we are going to perform this indirect function call. And this function call will jump to some special location that is filled with all retain instructions. So this call will retain immediately with no other side effect. However, Intel PT are going to dump a TIP packet into the trace. So the trace consumer on the other side are going to restore the ID by this function. So this way we can dump any non-control data into the PT trace and use it for our analysis. We abstract this instrumentation as a function called write data. So this way we can log any data into PT trace if it is necessary. And we can use such information to enable the analysis to infer the unique code target. So in our current setting, we just set the 4 million retain instructions. So this way we can log any data between -1K and 4 million -1K. So this is enough for our evaluation. So another question is what data is necessary to be encoded using our method? So we call them constrained data, which means non-control data that will indirectly affect the control flow. So we infer the constrained data in the following algorithm. So first, we find control data, which means a code pointer or a pointer of already known control data. So this recursive definition is very similar to the one used in code pointer integrity. So we use this recursive data flow analysis to infer all control data. And the second step, we find all the instructions that will manipulate on control data. We call them control instructions. So the last step, we find all the non-control data in these control instructions, and we believe them are necessary data to infer the unique target. For example, the array index here. So now we have a method to infer the unique target. So next challenge is how can we enforce the protection efficiently? Remember, the challenge is if you want to reconstruct the control flow from PT trace, it's pretty slow. So our idea is, can we avoid reconstruct the complete control flow? The answer is yes. We can avoid most of the past reconstruction. So the idea is we can assign a unique ID to each control instruction, and then we use our primitive to dump the ID into ptrace. So for example, in this code, we can insert the code like this to assign our ID to each interesting instruction and dump them into ptrace. So our analysis is very straightforward. So we just decode the ID from the trace, and then correspondingly we perform dynamic point-to analysis here. For example, if you know the ID 1, then we know the second line of code is executing, and we just update the point-to relationship for the array. So this way we can ignore all TNT packet in the ptrace. So to make this more efficient, we can, instead of assign an ID to each instruction, we can assign an ID to one basic block that have some control instructions. So this way we can do the analysis more efficiently. So now with this solution, we propose UCFI. We designed it as follows. It has two components. The first one is the UCFI compiler, which are going to compile the source code into a hardened version of the code. So the compiler are going to identify constrained data, are going to encode constrained data, and also encode the basic block ID into the program so that the ptrace can collect this information. And also the compiler also generates the LVMIR of the code and also a map between ID and the basic blocks. So at runtime, we have a monitor running at the same time with the execution process. So the execution process will trigger Intel PT to dump necessary data into the ptrace. And the ptrace is delivered through Linux kernel to the user space monitor. The monitor will decode the trace to find the basic block ID to know which instruction is being running. And it will decode the trace to find the constrained data for analysis, to perform point-to analysis to infer the unique target. And also for each indirect function call, it will check whether the target is consistent with our expectation or not. So our monitor are going to be synchronized with the execution of some critical system calls to make sure attackers cannot make a very severe attack to the program. So we implement UCFI on 64-bit system. The compiler is based on LVM 3.6. It's a LVM pass. And the monitor is like an LVM interpreter to infer the target. We also have a PD driver based on the Griffin code. So one important thing we want to emphasize is that we use the IP filtering provided by Intel PT. So you can just trace particular instructions in a particular memory range. So interesting part is we only trace one retain instruction and one indirect call instruction here to reduce the trace size. You can find the details in our paper. We evaluate our solution with benchmarks like spec benchmark and web servers and file servers with the default compilation options in this particular environment. So the first question we want to understand whether UCFI can enforce the unique code target property. So the answer is yes. We observe that at runtime, there is only one target allowed by UCFI. The question is, what if we do not have UCFI? What is the target in other case? So we also measure the number if we do not have UCFI. So here's the number here. For Go benchmark, it will allow up to 479 targets for some indirect function call. And for SG, it can up to 7 targets. And for each 264 ref, it can have more than 10 targets here. To understand why this is possible, this is the code snippet from SG. You can see the last line is the indirect call here, and the call target is calculated from an array of 7 function pointers. So previous work, including PDPAT, will allow any of these elements of the array. But our work will infer the unique one and only allow the particular target here. And also we want to understand whether our work can prevent the real-world attacks. So we collect 5 real-world attacks here, including heap overflow, stack buffer flow, and format string. They corrupt the code pointer or pointer code pointer. It turns out that all solutions, including previous PyCFI, PDPAT, and all UCFI, can prevent all of them because they are very standard attacks. And also to understand the effectiveness of UCFI, we also tried the Cooper attack. A POC used in PDPAT paper is a stack buffer flow will corrupt the pointer of C++ object. Turns out only PDPAT and our work can prevent this advanced attack. We also synthesize some attacks against the SG and Go benchmark to only corrupt the pointer to some allowed target by PDPAT. So this way, only our UCF work which enforce a unique target can prevent these attacks. So this evaluation shows that UCFI really can provide the strongest protection against the control flow hijacking attacks. We also try to understand the efficiency of proposal like memory overhead, performance overhead, memory overhead, and code size overhead. So this is the result of performance overhead. This is the comparison between PDPAT and our UCFI work. So the methodology is we just compare the overhead of the protected execution over the original execution. So on average, you introduce less than 80% overhead to spec benchmark, about 4% overhead to Nginx web server, and less than 1% overhead for VSIPTPD, which is a file server. But you can see for some benchmark, it could be have a high overhead for both PDPAT and UCFI, like the per bench. So the reason is that per bench will create a lot of process at runtime, and our monitor has to be forked at the same time. So we believe this is the reason for the high overhead. So we plan to optimize this in the future. We also measure the memory overhead and code size overhead. So the blue bar here is the memory overhead, orange bar here is the code size overhead. So you can see on average, so we have less than 1% overhead for spec, about 5.6 overhead for Nginx, and 4.8% overhead for VSIPTPD. We believe this memory overhead is acceptable for modern programs. Also, we measure the code size overhead. It's a little bit higher than memory overhead. It's 4% for spec benchmarks, and 20% for Nginx, and 70% for VSIPTPD. But from the figure, you can see there's a strong relationship between memory overhead and code size overhead. So we believe the code size overhead is the main reason of the memory overhead here. And we also found that there's a strong relationship between the code size overhead and the percentage of sensitive basic blocks. Remember that we only inserted the ID dumping into the basic block, which will have some sensitive instructions. So I guess this is why we have overhead here. So we also measure the trace size reduction in our PD trace. Remember that we do not have to use all PD trace to reconstruct the complete control flow of the execution. We only need part of it. So for each program, the left bar shows the original number of trace packet. So the right side is about the trace size used by our program. So you can see our trace is much smaller than the original one. That's why we can enforce the efficiency protection. So we also want to discuss a little bit about the backward edge protection, so which means how to protect the return address. So UCFI does not protect return address. We rely on existing proposals and solutions to protect the return address. So, but we do try to integrate our solution with one shadow stack proposal called parallel shadow stack. So in this parallel shadow stack, we do not claim any contribution or security or guarantee, just to check the compatibility of UCFI with the shadow stack proposals. So this work is, we implemented this shadow stack with 58 source lines of code in LLVM. And we measure the overhead of parallel shadow stack. It's about 2% overhead to this UCFI protected spec benchmark, and less than 1% overhead to Nginx and VSIPTPD. So we believe our UCFI is completely compatible with any shadow stack proposals. So we can replace this shadow stack with like SafeStack proposed in CPI and available in Kalam compiler. And also maybe in the future by Intel CET, which is a hardware-based shadow stack solution. So in conclusion, this work we propose UCFI, which are going to enforce the strongest protection against the control flow attack, which means that enforcing unique code target property. We combine both hardware and software design to make sure our protection is efficient. And one more good news is PD writing instruction is available. We do not have to use our emulation to dump any arbitrary data into the trace, which means our protection can be even faster. We plan to evaluate this in the future. And our code is already open sourced online. If you are interested, just feel free to try and let me know your questions. Okay, one advertisement. I'm on the job market this year, so feel free to contact me if you're interested. And thanks for your attention. I'm ready for questions.
Hi, John Criswell, University of Rochester.
Hi.
Nice work. So
Thank you.
From what I understand, this is a dynamic analysis approach in which you are inferring your targets through tracing, right, and then enforcing the unique target at runtime. Mm-hmm. So it seems to me that code pointer integrity, at least if properly implemented, prevents corruption of controlled data, as opposed to checking it. Mm-hmm. Therefore, your security guarantees should actually be identical, and then the only advantage really is performance. Would that be a correct assessment?
Yeah, thanks for the question. I have a slide for you. This is the comparison between CPI. So basically, okay, let's go through one column by one column. So basically, CPI will support any a 32-bit system and a 64-bit system. And currently, our solution is only for 64-bit system. And the most important difference is, I believe, is the protection stage is different. So CPI trying to prevent corruption in the first place, and our UCFI trying to detect any corruption when you have this indirect function call. And another thing is CPI currently only supports spatial corruption, spatial memory safety, which means like buffer flow or from a string, but for user-free and other temporal corruption, it's not blocked them yet. But our UCFI can block both type of corruptions. And isolation method, so the CPI will use a process to protect the sensitive data, which is secure. But for this 64-bit system, they use information hiding to try to hide the sensitive data.
Right. That's why I said properly implemented. Information hiding is not properly implemented in my opinion.
Right. Yeah, this is the difference of the CPI. And we want to see whether CPI can be implemented securely on 64-bit system with other mechanisms. But it seems there's no effort on this yet. But we are happy to see whether they are going to publish anything on this or not.
Okay, thank you.
Okay, thank you.
Hi, Zhou Jiaxun from University of Rochester. So have you applied this UCFI on operating system kernels? If not, what might be the challenge for doing that?
Oh, okay. Good question. Kernel is a very big program, and definitely we can imagine a lot of challenges on applying this on kernel, like the analysis. Maybe you need to generate a LVM IR program of the kernel and then apply this technique. But theoretically, there's no challenge to do that. But I would imagine it's a lot of engineering effort to fix all the compatibility issue and also some static analysis issue there. Yeah.
Okay, thanks.
Hi, this is Hong Liang from Intel Labs.
Hey.
Interesting work.
Thanks.
If I understand correctly, that you need to use some actual thread to at runtime analyze the logs.
Yes.
Right?
Yes.
So and your performance is acceptable, I think. But you have to consider that you have used actual CPU cores, right?
Yes.
Yeah. So in your benchmark, if you have one thread, do you have to use one dedicated thread to analyze the log?
Actually, the monitor is running a different process. Yes.
So if you have like a 4 threads execution in application, you have to use 4 actual threads.
Exactly.
So that means it's actually 2 times performance degradation, right?
It depends whether the monitor is active or not.
Oh, yeah, but if it's not active, then you can detect violation, right?
It depends whether the trace is generated for this particular execution or not. If you run a long blocks that have no sensitive information, basically no trace for that. But I do agree, we have extra CPU to do the protection at runtime.
Yeah. So you have the performance results, including how many actual CPUs that are.
No, we do not have that.
In the paper.
Yeah.
No. Okay.
Yeah. So the difference between this one and CPI, forget to mention that is we can do this protection in parallel with the execution. We believe this is also interesting. Previous work is you have to inline the checks into the execution.
Yeah.
And if you have a way to do them in parallel, that's interesting, I believe. Because in a lot of computers, there are so many cores spare around daily, so you can reuse them for your protection.
Yeah. Thank you.
Okay.
So I think my question is already asked. Thank you.
Okay. Thank you, guys.
I have a question.
Okay, go ahead.
So you just said your many cores are just idle, but there's a power issue, right? So very often you do not want to have those cores actually running because the power envelope of the chip is being affected by that.
I agree. Yeah.
Okay.
So if you have phones, be careful.
Okay. Thank you.
Okay. Thank you.